আচ্ছা, আজকে আমরা ম্যাক্সওয়েলের পোর্শনটা ইউনিট 1-এ একটা ইম্পর্টেন্ট জায়গা একটু দেখব। সেটা হচ্ছে মোমেন্টাম ডিস্ট্রিবিউশন। এটা এন্ট্রান্সের জন্য খুব ইম্পর্টেন্ট। মোমেন্টাম ডিস্ট্রিবিউশন কি হবে? আমরা স্পিড ডিস্ট্রিবিউশন আর এনার্জি ডিস্ট্রিবিউশন সম্বন্ধে দেখেছি ভিডিওসগুলোতে। আমরা আজকে মোমেন্টাম ডিস্ট্রিবিউশনের একটা কনসেপ্ট একটু দেখব। কিরকম? আমরা এখানে 1D আর 3Dটাকে এক্সপ্লোর করব। মোমেন্টাম ডিস্ট্রিবিউশন কিরকম? আমাদের 1Dতে ভেলোসিটি ডিস্ট্রিবিউশনটা কি ছিল? PU ইকুয়াল টু dnu বাই n ইকুয়াল টু m বাই 2 পাই kbt হোল টু দি পাওয়ার হাফ e টু দি পাওয়ার মাইনাস mu স্কোয়ার বাই 2 kbt। আর 3Dতে কি ছিল ডিস্ট্রিবিউশনটা? স্পিড ডিস্ট্রিবিউশনটা pc ইকুয়াল টু dnc বাই n ইকুয়াল টু 4 পাই ইন্টু m বাই 2 পাই kbt হোল টু দি পাওয়ার 3 by 2 e to the power minus mc square by 2 kbt multiplied by c square dc। এখানে একটা du ফ্যাক্টর ছিল, ডিউটা লেখা হয়নি। তো দিস ওয়ার দ্য এক্সপ্রেশনস। এইটাকে বলা হচ্ছে ভেলোসিটি ডিস্ট্রিবিউশন, and this is speed distribution. এবার আমরা এখানে যেটা করতে যাচ্ছি সেটা হচ্ছে একটা এনার্জি ডিস্ট্রিবিউশনের জায়গা। আমরা এনার্জি ডিস্ট্রিবিউশন আমরা করেছি, স্পিড ডিস্ট্রিবিউশন, ভেলোসিটি ডিস্ট্রিবিউশন জানি। তো আমরা এখন ভেলোসিটি ডিস্ট্রিবিউশন থেকে মোমেন্টাম ডিস্ট্রিবিউশন কি করে করব? এখান থেকে মোমেন্টাম ডিস্ট্রিবিউশন কি করে করব? মোমেন্টাম ডিস্ট্রিবিউশন কি করে করব? মোমেন্টাম আর 3Dতেও মোমেন্টাম ডিস্ট্রিবিউশন কি করে করব? এইটা হচ্ছে আমাদের কোয়েশ্চেন। তো এটা আমরা কিভাবে করব সেটা আমরা এগোচ্ছি। ঠিক আছে, চলো প্রসিড করব। এটা সরিয়ে দিলাম। তো ফার্স্ট অফ অল আমাদের যেটা দেখা দরকার সেটা হচ্ছে যে 1Dতে মোমেন্টামকে আমরা কিরকম ভাবে ডিনোট করব? মোমেন্টামকে আমরা স্মল p দিয়ে ডিনোট করব। স্মল p ইজ ইকুয়াল টু mu, স্মল p সাফিক্সে u ইকুয়াল টু মাস ইনটু ভেলোসিটি, মোমেন্টাম। তাহলে dpu ইকুয়াল টু m du, that means du equal to dpu by m. Substituting p probability suffix pu, AP stands for probability, AP stands for momentum, PPU, PU is momentum, only P is probability, is equal to m by 2 pi kbt all to the power half remains as it is, multiply by e to the power minus mu square, mu is P, means PU, multiplied by mu square means mu multiplied by u. Mu is pu. Now what is the value of u? The value of u is pu by m. So you have got another pu by m. Mu square means mu multiplied by u. Mu is pu. U is pu by m divided by 2 pi kbt. 2 kbt. Multiplied by du. What is the value of du? Du is dpu by m. So it becomes m to the power half in the denominator. It becomes m to the power half in the denominator. So you can write it like this. 1 by 2 pi m kbt whole to the power half goes in this way. And then you have this term a to the power pu square divided by 2m kbt multiplied by dpu. So this is the probability of finding a molecule within the momentum pu to pu plus dpu. This is the probability. So what is the probability per unit interval? If we divide this by dpu, we'll get the probability per unit interval. So if you have to divide this particular term p of pu by dpu, so that you will get the probability per unit interval. So divide it. P dash pu is basically p pu divided by dpu. So it becomes this term 1 by 2 pi m kbt whole to the power half e to the power minus pu square by 2m kbt. What do you find? You find the same type of variation in comparison to the velocity distribution. In velocity distribution, you find a Gaussian decay e to the minus mu square by 2 kbt. Here also you'll find a Gaussian decay. So the curve remains as it is, Gaussian. The curve remains as it is, it's Gaussian in nature. It's Gaussian in nature. Okay. Now let us see what is happening for this particular case. So let us erase out the velocity part. So now we'll be doing the speed part. So in speed distribution, we'll write momentum as Pc. Or better to write in this way. Better to write Ct. Momentum in 3D. What is the value? mc. And dp3d is equal to mdc. So these are the conversion factors. Therefore, P of P3D is equal to what we will have? The constant will remain as it is. 4 pi multiplied by m by 2 pi kbt, that will remain as it is. It will not change. So 4 pi multiplied by m by 2 pi kbt whole to the power 3 by 2. This is a constant factor. This will remain as it is. Here again you have MC multiplied by C. What is the value of MC? P3D. So you'll write it in this way, e to the power P3D multiplied by C. What is the value of C? P3D by M. So you write it in this way, P3D divided by M divided by 2 kBT, which remains as it is, multiplied by C square. What is the value of C square? P3D by M whole square. Multiplied by DC. What is the value of DC? Value of DC is dP3D by M. See, this factor remains as it is. E to the power MC is P3D multiplied by C. C is P3D by M. 2 kBT remains as it is. Multiplied by C square. What is the value of C? The value of C is P3D by M. So it becomes P3D by M whole square. And what is the value of DC? DC is clearly P3D by M. dP3D by M. So I have substituted all the values. So what will I get? See, we are getting 4 pi. Okay. Now what is the power of M? The power of M is 3 in the denominator and 3 by 2 in the numerator. So the power will become effectively 3 by 2 in the denominator. So this becomes 1 by 2 pi M kBT whole to the power 3 by 2. Power of M in the denominator is 3 and power of M in the numerator is 3 by 2. So power in the denominator becomes 3 by 2. So 1 by 2 pi M kBT whole to the power 3 by 2 multiplied by e to the power minus P3D square by 2M kBT multiplied by P3D square dP3D. So again you will find that the curve is exactly same as the speed distribution curve. Initially you have a parabolic rise that would be followed by a Gaussian decay. So you'll have a parabolic rise that would be followed by a Gaussian decay. That's what we find in case of speed distribution. So it exactly emulates the speed distribution curve. So you'll be getting, if you are plotting P dash P3D, which is nothing but P3D PP3D divided by dP3D. If you are doing that, you are dividing by this term. So initially you will be getting a parabolic rise that would be followed by a Gaussian decay. Then here you will have P3D most probable value. And here you will have P dash P3D max. So the curve is exactly same. Parabolic rise, which is followed by Gaussian decay. So we'll try to evaluate the value of P3DMP. Exactly. But in our previous lectures, in the previous lectures, I have shown that energy at C equal to CMP is not equal to epsilon MP. Energy at C equal to CMP is not equal to energy at a most probable energy. But let's check whether P3D at C equal to CMP is equal or not equal to which one? With respect to P3D MP. Now, what is our perception? Our perception is, in case of energy distribution, the curve was different. In case of energy distribution, there was a parabolic rise, but the parabola was not like this, y proportional to x square. The parabola was y proportional to x to the power half. So, in case of energy distribution, the curve looked a bit different. This was the parabola. And here, in this case, the parabola is like this. And here, the parabola was like this. Okay, it's a convex type of a parabola. And this is concave type of a parabola. And again, the decay was exponential in nature. So this was epsilon mp. Although qualitatively the nature is same, there is an increase followed by a decrease, but the nature of increase and the nature of decrease is quite different from this one. That's why what happens is, this term, I'm sorry, if CMP doesn't match with this one. But in this particular case, we find that the nature of the probability distribution of momentum is quite similar to that of the speed distribution, because the parabolic rise is also same as that of the speed distribution, and the decay is also Gaussian in nature. So it is expected that these two values should be same. So let us check whether they are same or not. So for that purpose, what we need to do, we need to find out the expression. So as we already know that in order to determine the maxima, what we need to do, we need to differentiate this with respect to 0, and then we need to equate it, differentiate it, and we need to equate it to 0. So d p dash p3d divided by d p3d, this one. So what is the value? You have a constant, and don't write the constant over and over again. So you have a constant. The constant is pulled outside the differentiation, and within the differential you have these two terms only. This is not there because you have divided by dp3d. So that goes over here. So upon differentiation, what you'll see, the exponential term will be repetitive, c3 square by 2m kbt. Okay. Now, you again need to differentiate this one. So if we differentiate this, minus 2p3d, this 2 will cancel out. So you're getting minus p3d by m kbt. Got it? Multiplied by p3d square, because p3d square will remain as it is. So if you multiply this by p3d square, it will become p3d cube. Multiplication rule. You are differentiating this one, you are keeping this one constant. Now, you will be keeping the exponential term constant, e to the power minus p3d square by 2m kbt. You will hold the exponential term constant, and you will differentiate this one. If you differentiate this one, you will get 2p3d. That's it. Now, you need to pull this one and this one out, and also 1 p3d. So what you are doing, you are writing constant multiplied by e to the power minus p3d square by 2m kbt multiplied by p3d. So what you are getting, minus p3d square by m kbt plus 2. Say we are calling this slope to be m. This is the slope. We are calling the slope to be m. So we know that at maxima, this m is equal to 0. Slope is equal to 0. Let us write the slope as m dash, or else it will be a problem. Mass is also written as m, na? That's why we will write the slope as m dash. So let us consider the slope to be m dash, and we'll see that the slope is reduced to 0 at maxima. This is the condition. So you have three options over here. Either you can equate this to 0, or you can equate this to 0, or you can equate the entire thing within the bracket to be equal to 0. Now it is not possible for this to be 0, because for this term to be 0, P3D MP should be infinity. But we find that P3D MP is not infinity. So P3D MP is not equal to infinity. So this option is eliminated. Neither P3D MP is equal to 0. If this is 0, then P3D MP is 0. But P3D MP is not 0. It's somewhere over here. It's not over there. So again, not 0. Not 0. So the only option with which we are left is equating this to be equal to 0. If this is equal to 0, that means this term is equal to 2. This term is equal to 2. That means P3D MP is equal to 2m kBt. P3D MP square, sorry, is equal to 2m kBt. P3D MP square by m kBt is equal to 2. That means P3D MP square is 2m kBt. That means P3D MP should be equal to root over of 2m kBt. Got it? Got it. Now, let's rub this off. Now, let us check whether C at CMP, P3D at CMP is equal to P3D MP or not. So what is the value of P3D at C equal to CMP? P3D is nothing but M multiplied by C. Here C should be CMP. P3D at C equal to CMP is nothing but M multiplied by CMP. So you substitute the value of CMP over here. You substitute the value of CMP over here, M multiplied by root over of 2 kBt by M. And that is nothing but 2m kBt. So you can see these two are same. Why they are same? Because the nature of the curve is same. But in case of energy distribution, we found that they are not same. Okay. So this is a very interesting observation. This is a very interesting observation. Actually, the process is all the same. You can convert it into energy, you can convert it into momentum, or anything related to speed. Now, what is the maximum value? What is this value? I have to calculate this value. This is done. This is root 2m kBt. I found this. So P dash P3D max is basically equal to 4 pi, it's there, multiplied by 1 by 2 pi m kBt, that is there, whole to the power 3 by 2, Just you need to replace this P3D by P3D-MP. So e to the power, what is the value of P3D-MP? The value of P3D-MP is root 2 mkBT. Now if you substitute here root 2 mkBT, then there is a square, so it becomes 2 mkBT, and 2 mkBT is even there in the denominator, so it becomes e to the power minus 1. That means 4 pi by e. So you don't have this one. It becomes e to the power minus 1, just replacing P3D by root 2 mkBT because it's the most probable momentum. Now what is the value of P3D square? Once again, it's 2 mkBT. So you write it 2 mkBT. Yes. So you have basically, if you infuse pi over here, then you have 1 by 2 pi mkBT whole to the power 3 by 2 multiplied by 2 pi mkBT. That means the power of 2 pi mkBT becomes half in the denominator. So it becomes 4 pi by e square root of 2 pi mkBT. Oh, pi would not be there. 4 by e. So this is the answer. So there can be a lot of problems coming out of this. So you can calculate these things from here. Now we'll study a very important topic. It's a bridging topic, and the topic is known as barometric distribution law. This part is not included in semester 1, but this part is related to kinetic theory of gas. This is barometric distribution law. In some colleges they teach this thing, barometric distribution law. What does this thing reveal? It reveals the variation of pressure with altitude. So it determines the variation of pressure with respect to altitude. Exactly. So we'll try to deduce this in a different way. So for this purpose, what we need to do, we need to consider an axis, a reference axis. The reference axis which measures the altitude is z axis. This is chosen to be the reference axis. The ground level is considered to be z equal to 0. This is the sea level, where we consider the pressure to be P equal to P naught. In this case, we'll be constructing a uniform cylindrical air column. Okay, we'll be constructing a uniform cylindrical air column. So you have constructed a uniform cylindrical air column, so it looks like this. This is the uniform cylindrical air column. If it's a uniform cylindrical air column, then its cross-sectional area is constant. the cross-sectional area is supposed to be A. I'm telling that Z is any height Z. We're choosing any height Z. We're choosing any height Z. It's an arbitrary height Z. An arbitrary height. So you need to calculate the value of the pressure at height Z. You need to calculate the value of Pz, which is written as P, simply written as P, equivalent to P. So you need to find out an expression of P at any height Z. And what assumptions are we making? Assumptions. We're considering ideal gas. We're considering constant temperature and acceleration due to gravity. We're considering constant temperature and acceleration due to gravity. Third, area A is constant. That means uniform air column. So these constraints are maintained. So you need to find out an expression of P at height Z. Let us consider another layer, Z plus dz. The gap is dz. And let us consider the pressure here to be P plus dP. At Z, we are considering the pressure to be P, and at Z plus dz, we are considering the pressure to be P plus dP. Now, how do we calculate? How do we calculate pressure at any height Z? Pressure means force per unit area. So the force is the weight of the air column till this level, the weight of the air column, till this level, weight of the air column till this level, divided by this area. So let us consider the mass of the air column to be m over here. Mass of the air column above height Z to be m over here. So what should be the expression of P? P is weight divided by area. And in this case, the mass is this much. The mass is lower than this one. Let us consider it to be m plus dm, where dm is negative. Writing in this way, because the mass of the air column above height Z is obviously greater than the mass of the air column above height Z plus dz, because it is counted right from the top. So if you are increasing the height, obviously the mass decreases. And this is natural, because if mass decreases, then the weight decreases, then the pressure decreases. So obviously with increase in height, you'll have a lowering of pressure. So this m is negative. What does that imply? That implies m minus mod of dm. So P plus dP should be equal to m minus mod of dm multiplied by G by A. Mass into acceleration due to gravity divided by area. So that means P plus dP should be equal to mg by A minus mod of dm G by A. But mg by A is already equal to P. mg by A is already equal to P. So obviously these two terms will cancel out. And what you find? You find the generalized differential equation to be minus mod dm multiplied by G by A. And we all know that mod dm is positive, G is positive, area is positive. Dp is negative because you have a minus sign in front. So negative multiplied by positive is negative. So obviously this dp is negative. That means change is negative. That means with increase in height, P must decrease. Thereby the change is negative. Okay. Clear? Now let us find out the expression of mod dm. What is mod dm? Mod dm is basically the mass of the air enclosed within this space. Mass of the air enclosed within this particular space. This is mod dm. Mass of the air enclosed between height z and z plus dz. That is mod dm. So how to calculate that? Mass means density multiplied by volume. So what is the volume of this space? Volume means area multiplied by height. Height is dz. So volume is A multiplied by dz. So you have got A dz. This is volume. And let us consider density to be rho. So it becomes rho A dz. Thereby, you can see dp is becoming equal to minus mod dm. So minus, what is the value of mod dm? Rho A dz multiplied by G by A. A will cancel out. And the differential equation turns out to be dp equal to minus G rho dz. Understood? Now, at first, we consider a hypothetical situation where rho is constant. At first, we will consider a hypothetical situation where rho is constant. This is hypothetical because we all know that with increase in altitude, the atmosphere gets rarefied and the value of rho must decrease. In the sea level, the density is very much high, but as we go to the top, the density of gas decreases. There is rarefication of atmosphere. So rho will decrease. But at first, we are considering a hypothetical situation where rho is held constant. Okay. So What is our observation? If we consider rho to be constant, g is already a constant. So this integration becomes very easy because in this particular case, here dp is integrated from p naught to p. Here minus 0 is a constant, so it is pulled out of the integration. And here integrating dz. At z equal to 0, the value of p is p naught, and at z equal to z, the value of p is p. So this happens to be a very simple differentiation. So it becomes p minus p naught equal to minus 0 dz. That means p equal to p naught minus 0 z. So getting this? Now what does this imply? This implies that if we vary p with respect to z, what we'll get? We'll get a decrease, but a linear type of decrease. Because if this is plotted along y-axis, z is plotted along x-axis, then the slope, this is the slope, and this is the y-intercept. Okay. So the slope is p naught, and the y-intercept is, I'm sorry, the y-intercept is p naught, and the slope is minus 0. So the slope is negative. That means there is a linear fall. So this implies, this hypothetical situation implies p decreases linearly with z. But actually this is not happening. Actually this is not happening. Why? Because that rho is not constant. So if we consider ideal gas, that is also a hypothetical situation, but more practical than this one. This is absolutely absurd. Considering ideal gas is a bit absurd, it's a bit more oversimplified, but still we can consider it to be an ideal gas rather than considering it to be a hypothetically like this, rho is constant. So in this case, we will consider the gas to be ideal in nature. And if the gas is ideal in nature, then what should be the expression of rho? What should be the expression of density? We all know that PV is equal to N RT. N is nothing but mass by molar mass multiplied by RT. So if we take these two terms together, then mass by volume is PM by RT, and that is nothing but rho. Number of moles is mass by molar mass multiplied by RT. So mass by volume is density. So mass by volume, taking these two terms together, first and the third term, equating them, we are getting P by RT multiplied by molar mass. So let us substitute PM by RT in place of rho. Let us do this. So what are we getting out of that? dP is becoming minus G multiplied by rho. Rho is PM by RT multiplied by dz. So what you are getting, dP by P equal to minus Gm by RT multiplied by dz. Okay. Now already we have at z equal to 0, P is P0, at z equal to Z, P is P. And this term is constant. Why? Because G is constant, we have already considered it to be constant. Molar mass of the gas is always a constant. Of that particular gas, the molar mass is a constant. Capital R is a universal gas constant, so that is also constant. And we have considered the temperature to be constant. So it varies from 0 to Z. In fact, temperature will also vary with altitude, but that is a separate issue. We'll study that in thermodynamics, not here. Here we'll consider temperature to be constant, but temperature varies. That is the part of thermodynamics. In thermodynamics also we'll be using this particular equation only, but the treatment will be a bit different. So we have got this equation. Now what is the integral of dP by P? Log ln. So you are getting ln P by P naught to be equal to minus Gm by RT multiplied by Z. So what you are getting? P equal to P naught multiplied by e to the power minus Gmz by RT. I take the exponential. So getting a first order type of decay. First order kinetic type of decay, in exponential decay, e to the power minus Gmz by RT. So how does it look like? If you are plotting P against Z, you'll find an exponential decay starting from P naught. At Z equal to 0, P is equal to P naught. You'll find an exponential decay. So it leads to an exponential decay. Now suppose this exponential decay occurs at temperature T1. And if you increase the temperature, say you are doing it at another temperature T2, if T2 is greater than T1, then what will happen? Why? Why? This is your equation. Now suppose if you are increasing the temperature, what will happen? See, if you are increasing the temperature, then this term will increase, denominator increases, so this entire fraction will decrease, but again there is a negative sign in front, so the entire thing will again increase. Denominator increases, so what happens? Gmz by RT decreases, but you have a negative sign in front, so minus Gmz by RT increases. So e to the power minus Gmz by RT increases, thereby the entire thing increases. So with increase in temperature, the pressure increases. So with increase in temperature, you'll see P increases. So high temperature line runs above the low temperature line. So high temperature line is going to run above the low temperature line. Even if you higher the temperature by say T3, again T4. So this looks like this. So what is happening? You have to understand. with increase in temperature, you see that the curvature of the exponential decay gradually decreases. The curvature of the exponential decay gradually decreases, and the exponential decay gets a linearized nature. With increase in temperature, the curvature of exponential decay decreases and it attains a bit of linearity. So with increase in temperature, linearity is approached. The question is why? You have to understand the thing mathematically and physically as well. So at first, we will have a mathematical interpretation of this. Why at all this is happening? Why at all this is happening? So we'll start from this equation. We'll start from the generalized equation, the generalized exponential equation. What is the equation? The equation is P is equal to P naught multiplied by e to the power minus gmz by RT. This is the equation. And we all know that e to the power minus x is 1 minus x plus x square by factorial 2 plus, minus x cube by 3 factorial plus x to the 4 by factorial 4 and so on. So you can write it in this way: P naught whole multiplied by, here this is x, so 1 minus gmz by RT (1 by factorial 2 gmz by RT whole square minus 1 by factorial 3 gmz by RT whole cube plus 1 by factorial 4 gmz by RT whole to the power 4 and so on. It runs in this way. Now, in this case, if x is very small, if limit x is tending to 0, then we will neglect the higher order terms and it becomes 1 minus x. So, limit t tending to infinity, if t is very high, then p is equal to p naught multiplied by, you see, if t is very high, then gmz by RT is very low. So the situation is similar. Here x is gmz by RT. So if you increase temperature, then gmz by RT becomes very low. That means x is very low. So what will happen? You don't have any higher order terms, you just have the first order term. So you are getting p naught whole multiplied by 1 minus gmz by RT. And that is nothing but a straight line. You don't have any higher order power, just have power 1 for the variable z. So at very high temperature, it is automatically attaining a linearity. So this is the linear nature. So this is quite understandable from the viewpoint of mathematics. But can this be interpreted from the physical background as well? Can this be interpreted from the physical background as well? See, it was linear when density was constant. And it is exponential when density is a function of pressure, Pm by RT. If density is constant, it is easily pulled out of the integration and you are getting a linear type of decay. And if density is a function of pressure, then you don't have that. So, is there any mechanism to relate these two things together? See, if we increase the temperature, what will happen? If we increase the temperature, then the kinetic energy of the gas molecules will increase. And as the kinetic energy of the gas molecules will increase, what will happen? The gas molecules will become completely random. And as the gas molecules becomes completely random, then what will happen? The probability of occurrence of the gas molecules of the entire space will become same, because the gas molecules have become random. It will no longer settle at the bottom more and go to the top less. That will not happen. What will happen? It will form a randomized current. And as it forms a randomized current at high temperature, what happens? The density starts becoming uniform. So what you are doing, you are creating such a situation that this realistic situation is turning out to be the hypothetical situation where density was constant. Yeah, you are increasing the temperature, and as you are increasing the temperature, what happens? Due to the randomized motion, the density is attaining uniformity. And as the density attains uniformity, what happens? As the density attains uniformity, it will attain the linearized nature. So this is the physical reason. So we'll write it. With increase in temperature, the motion of the gas molecules become random. Motion of the gas molecules become random, and rho density attains almost uniformity. So a linear nature is achieved. So this is the reason of attainment. This is the physical reason. This is the physical reason. This is the physical reason, and this is the mathematical reason. যদি এরকম জিজ্ঞেস করে যে at what height এরকম যদি জিজ্ঞেস করে at what height P becomes half of P naught. মানে এটা বলা হচ্ছে P ভার্সেস Z প্লট করা হয়েছিল। This is P naught. এখানে P equal to P naught by 2 হলে what should be the value of Z? This is being asked. Temperature is constant, T, G, M, these things are constant. Exactly. And you have to find the result in terms of T, G, and M. And if they provide the values of T, G, and M, then suppose at what height P becomes half of P naught, given helium gas at 273 Kelvin. Suppose this is given. It's very simple. Yes, write P equal to P naught multiplied by e to the power minus gmz by RT। এটা দেওয়া আছে, বুঝতে পারছো? এই হিলিয়াম গ্যাসের টেম্পারেচারটা দেওয়া আছে, বলে দিয়েছে তোমাকে। আমি অঙ্কটা করে দিচ্ছি, ভ্যালু বসানো তোমাদের কাজ। তাহলে এখানে পি জায়গাতে কত বসাবো? পি নট বাই 2 বসাবো। অঙ্কটা খুব সোজা কিন্তু, ই টু দি মাইনাস gmz বাই RT। জেডটাকে জেড হাফ লিখছি, জেড হাফ মানে একটা রিপ্রেজেন্টেশন, সাফিক্স হাফ। এখানে হচ্ছে জেড ইকুয়াল টু জেড হাফ। তো পি নট ক্যান্সেল আউট। লগ নিলে কি হবে? এটা এলএন হাফ মানে কত? মাইনাস এলএন টু, মাইনাস এলএন টু, এটা মাইনাস জিএম জেড হাফ বাই RT, মাইনাস মাইনাস ক্যান্সেল আউট। এলএন টু মানে 0.693, তাহলে জেড হাফ ইকুয়াল টু 0.693 RT ডিভাইডেড বাই GM। বাস, ইউ নো দ্য ভ্যালু অফ আর। এসআই তে করছো, আর এর জায়গাতে 8.314 জুল কেলভিন ইনভার্স মোল ইনভার্স বসিয়ে দেবে। হ্যাঁ, এক্সামে ক্যালকুলেটর দেবো ওরা। যে যে আমরা আমাদের অ্যাপে যে ক্যালকুলেটর দেবো সেইটা, ওরা সাইন্টিফিক ক্যালকুলেটর হাতে না, ওরা অ্যাপে দিয়ে দেবে ক্যালকুলেটর। জ্যামে ক্যালকুলেটর হাতে দিয়ে দেবে তোমাকে। এই ক্যালকুলেটর নিয়ে যেতে পারবে না, তোমাকে ওই অ্যাপের মধ্যে ক্যালকুলেটর দিয়ে দেবে। আর সেই ক্যালকুলেটর কি ক্যালকুলেটর সেটা আমরা প্র্যাকটিস করাবো। টেম্পারেচারটা 273 কেলভিন বলে দিয়েছে, দেবে দেবে। জিটা হচ্ছে 9.8 মিটার পার সেকেন্ড স্কোয়ার। সব এসআইতে করছি। মোলার মাসটা কত? হিলিয়াম হচ্ছে 4, কিন্তু কেজিতে করতে হবে, ওটা 4 গ্রাম পার মোলায়, কিন্তু এসআইতে তোমায় কেজিতে করতে হবে। হ্যাঁ, 0.004 কেজি পার মোল। তো এইগুলো সাবস্টিটিউট করলে উইল গেট দ্য ভ্যালু অফ জেড অফ ইজিলি। লজিকটা ঠিক আছে না? বোঝা যাচ্ছে তো? তো এই অবধি ছিল, দেখো।